upper atmosphere, only a small amount of radiation is emitted from the upper part of the atmosphere, as we described earlier. Now, the effect of the main absorbing layer, the troposphere, of course, is to reduce the long wave radiation going out to space for a given temperature. When we looked at the black body radiation equations for the grey atmosphere, for example, that's what we assumed. So if we were to reduce the outgoing long wave radiation, obviously the planetary atmosphere is going to heat up until it establishes equilibrium. And that equilibrium is going to occur when the absorbed solar radiation at the surface balances the outgoing long wave radiation. Remember our discussion about the balance between the incoming at the surface and the outgoing at the top of the atmosphere. In other words, the surface flux Fs has got to be equal to, eventually, the outgoing long wave radiation budget. But we have to remember that this outgoing long wave radiation, following some kind of perturbation that leads to an increase in temperature, is going to be reached somewhat higher in the atmosphere, the cooler, thinner parts of the atmosphere, not at the surface. So if we keep adding greenhouse gases, that tau equals 1 level is going to be shifted to higher and higher altitudes, where of course it's colder. If we remember our Stefan Boltzmann law, then of course that region is going to emit much more feebly because essentially it's colder. So we have this temporary result where the energy in the system is greater than the outgoing long wave radiation until we can establish that equilibrium at some higher temperature. Okay, so let's remind ourselves of how we approach these very simple greenhouse gas models of the atmosphere. We talk about greenhouse warming, we can think about the surface as simply related to the effective surface temperature, or the effective system temperature, I should say, which of course is the temperature of our black body that would emit the same total amount of electromagnetic radiation, plus this additional term, which is simply a product of gamma, which we said was the rate of change of temperature with height, so dTEZ, times the height at which that outgoing long wave radiation essentially occurs. In other words, the tau equals 1 level. So remember, gamma is the lapse rate, the rate of change of temperature with height. H is the height of this emission level, if you like. And remember, the atmosphere radiates upwards and downwards. So we have to write the energy budget as essentially the sum of those two products in our simple model, one upwards, one downwards, so 2 sigma t to the 4th. And that, of course, has got to be balanced by the energy budget at the surface, sigma t to the 4th, where t there is now the surface temperature. But of course, we also include this epsilon term to take into account that we're not really dealing with a perfect black body. Now, of course, the surface is heated by both incoming shortwave solar radiation, or a fraction of it. Some of it's reflected by various components in the atmosphere and the surface itself. But of course we've got this extra downwelling radiation from the absorbing atmosphere. So the budget is essentially this term, plus the incoming shortwave, plus this extra long wave term from our black body atmosphere, or near black body atmosphere, E sigma t to the 4th, where t is the atmospheric temperature. So that's how we can relate the surface temperature to the atmospheric temperature. Remember, E in this case is just a fraction to take account of the Earth not being a perfect black body. So that is the sort of picture, the conceptual picture that we have, where we can plot the temperature as a function of altitude. So the rate of change of temperature with altitude is just that gamma term. And let's assume, of course, that that's for a given CO2 concentration in the atmosphere. And of course, this line here is going to represent the effective emission height. We talked about the tau equals 1, where the long wave radiation goes out to space. But what we now want to do is, of course, suddenly increase the CO2 concentration. So in response, the system is going to eventually warm up, leading to an increased temperature across the entire atmosphere. Let's assume it's the same lapse rate. So the surface temperature goes up by an amount delta T, and also in response the effective emission height is going to go up by another small amount delta H. So that's a simple concept that we have to keep in mind. So, what are the factors that might alter that radiative forcing that we're sort of talking about here? Well, when we talk about radiative forcing, we tend to separate them into radiative forcings RF plus feedbacks. Now, radiative forcing is an energy imbalance, so remember that. It's going to be imposed on the climate system somehow. Could be externally from, say, changes in incoming solar radiation, or it could be from increased emissions of anthropogenic warming, greenhouse gases. But the feedback is an internal response to the system to the climate change. Now, the problem is that you can both get amplification or dampening in terms of the response. So one has to look at those very carefully. Now, you should know that over the last few years, this radiative forcing concept has received some criticism in the scientific community. Why? Well, because it's got very limited ability to account for climate changes on local or regional scales. So you can get big changes on very small spatial scales, but they don't really have a big impact across the globe. For example, changes in the hydrological cycle, and indeed many aspects of aerosols in the atmosphere. For example, aerosols can have a positive top of the atmosphere radiative forcing, but overall, globally, they will end up cooling the surface. So that has led people to look at the lifetime, if you like, and the spatial extent of radiative forcing more recently. But by and large, it doesn't change the picture very much. So, radiative forcings that we are going to describe here are still a very useful first order method to quantify the impact of a given change in our system. We might change the boundary layer system, the boundary layer conditions in our system, for example, which produces some change. And we're going to look at that change, obviously, as a function of some kind of perturbation to the system. And we're more interested in the changes due to greenhouse gases, and specifically carbon dioxide here. And based on lots of model calculations, this is the basic equation that you try and remember for a given change in radiative forcing and the change in radiative forcing that it produces. So F, the change in radiative forcing in watts per meter squared, is simply 5.35 times the log of C over C naught. I'm sure you can all remember that. C and C naught are the final and initial concentrations of our greenhouse gas, in this case the CO2. Obviously the units don't really matter because it's a ratio. So if we were to start off with some pre-industrial concentration and then ratio that to the current concentration, we can get the change in radiative forcing as a result of anthropogenic emissions, for example. Now remember that response to successive increments in CO2 changes becomes progressively smaller as CO2 increases, because remember each doubling, for example, produces the same forcing. So going from 50 to 100 has the same effect as going from 1,000 to 2,000. But it's the additional radiative forcing we're interested in here. So if we were to, for example, double CO2 from whatever to whatever, then it's easy to see that the radiative forcing is going to be of the order of 3.7 watts per meter squared. And if you look at that very small number, to put it into context, it's very similar to about a 2% increase in total solar irradiance. So we're looking at a small number here, but it has significant consequences. So let's go back to our very simple model. So we have our top of the atmosphere where we have incoming solar and outgoing long-wave radiation. And the budget equation is shown there. So the flux out minus the flux in. And we're going to set that equal to the net radiation, or in this case minus, because we want to put that sign in to be able to say, well, there's a positive or negative forcing at the end of the day. So minus delta I. Of course, if the system is in perfect equilibrium, then flux out equals flux in, so delta I in this case is going to be equal to 0, the net radiation. If we suddenly double CO2, Well, conceptually we know it's going to reduce the outgoing long-way radiation, leaving the top of the atmosphere. Let's assume it changes it by an amount delta I, so that's the change in radiative forcing. That change in radiation has got to be balanced at the top of the atmosphere, so the Earth's surface temperature has got to rise. And let's assume it changes by an amount delta Ts to compensate for that sudden change. So what we've been talking about here now is the concept of radiative forcing. We're forcing the system to respond to our doubling of CO2. Now in reality, of course, the response is examined very carefully with a very large complex global climate model. If we run the climate model with and without a particular variable in them, so we might have a particular variable suddenly perturbed, and we look at the comparison between that and the unperturbed system and look at the impact it has on, for example, the temperature. And then we can link that to the change with respect to radiative forcing. So, in our very simple model, let's assume the flux increase F is simply delta I. That's going to be connected to an increase in, we know the effective temperature of the system, so let's assume that that change in effective temperature is delta Tf. And the equation we can write is simply F equals delta I, and that's proportional to delta Tf, and the derivative of the radiation with respect to the effective temperature. Remember, I is normally the intensity of the Earth's radiation, which we normally measure at the top of the atmosphere in these sorts of radiative forcing examples. So, I'm sure you can all differentiate. I, remember, is given by that term, the Stefan-Boltzmann law, sigma t to the fourth, with an epsilon in there usually. So let's differentiate that, and we get 4 epsilon sigma t cubed. And of course we can simply rewrite that as the original expression for I, 4 times I divided by the temperature. And if we assume the incoming solar radiation on average is just the solar constant divided by 4 multiplied by 1 minus the planetary albedo, which we discussed earlier in the course, then of course we can calculate that term, di dt. That comes out to be about 3.1 watts per meter squared per Kelvin. Now we then want to try and rearrange this equation up here for delta I. In other words, let's write it in terms of delta Tf. Well, it's simply going to be 1 over di dt times delta I. And we're going to rewrite 1 over di dt as this function here, g. Of course, delta I is just the same as f up there, so effectively our equation is g delta I or gf. Now g in these equations is what we call the gain function. So if we're effectively looking at the link between the cause and the ultimate effect. So of course the cause here is going to be a change in radiation versus and the effect is going to be a change in temperature. So remember our gain function here in this particular example is about 0.32 per watt meter squared Kelvin. And from our previous calculation, from that equation for a doubling of the CO2, so put the equations back up, you can calculate that the forcing, the change in that radiation, is going to be about 3.7 watts per meter squared. And from this equation, putting 3.7 in here, we can estimate that the change in the effective temperature of our system is going to be about 1.1 Kelvin. That's a very rough calculation, but it's actually a pretty good approximation. And remember, this is just for CO2. It doesn't include any of the other potential forcing agents in the system. So, if we remind ourselves about what CO2 is doing, pre-industrial, remember, it was about 280 parts per million, 2003, 375 parts per million. Today it's over 400, approaching 410. And just to remind you about the lifetime effect of CO2, which we're not going to be too worried about in this course, but remember, since 1850, 43% of the carbon that's actually emitted into the atmosphere remains in the atmosphere. It has a long lifetime, over 100 years. It's generational. The remaining, about 57%, is stored in the oceans, and the terrestrial biosphere. There's some discussion about the relative storage between the ocean and the biosphere, but roughly 57% in total. But of the amount that's put into the atmosphere, almost 2/3 has been added by fossil fuel burning. The rest is due to land use change, deforestation, and so on. So, using that simple equation, you can calculate the change in temperature from pre-industrial to, for example, not 2003 in that graph, or 2017 or 2017, and it's roughly about 0.6 degrees Kelvin, 0.5 to 0.65 degrees Kelvin, approximately. Remember, that's just the temperature change that would result from CO2 in the atmosphere. We're not talking about any of the other greenhouse gases which would also contribute. So this is an old prediction by the UK Met Office, where they essentially made a projection based on current measurements, which in that case was in this 2010 report, 2005 data. So the Vostok ice core, as you can see there, shows our CO2 concentrations changing through the so-called natural cycle over the last 450,000 years. We talked a lot about these various perturbations. These are coolings, cooling arising from reduction in solar fluxes linked to the Milankovitch cycles, which end up reducing CO2 in the concentration during the glacial periods, increasing the CO2 during the interglacial periods. But now, of course, we've got the reverse happening, where suddenly man comes along and has perturbed the system and has essentially taken a lot of that stored carbon and put it into the atmosphere. And that model calculation estimated that under current scenarios of emissions, we'd end up with well over 650 parts per million of CO2 in the atmosphere by the end of this century, by 2100. So if we were to take that estimate of 6, in this case 75 parts per million, compared to pre-industrial concentrations, the change in temperature just due to CO2 enhancement alone is going to be about 1.5 degrees Kelvin. Now that's a prediction based on a particular scenario, so there's uncertainties associated with it. Okay, we alluded to something called feedback on the system, and we looked at a very simple one in terms of the change in the height at which the radiation is being emitted, and the response in terms of the temperature throughout the atmosphere and then the surface temperature. But of course, changing surface temperatures will affect many different variables in the surface system, and those might respond in many different ways, and some of them can either reinforce the warming, or in fact it might actually counteract it in some way. And we tend to use what are called feedback mechanisms to describe the magnitude and timescales over which those changes might occur. And that's a very simple figure you've probably seen many times before if you've done electronic circuit theory, etc., etc. This is just a picture of a very simple feedback loop. So this is a single feedback loop where part of the output of this system is going to be fed back to the input. So we start out with some signal, in this case Vs, enters this feedback loop, and then ultimately it's going to receive an extra input from the system, which in this case is going to be essentially an increase in the signal Vs by adding on this extra value here based on a fraction h. So a signal Vs enters the loop, it receives an extra input, which we're going to call Vf, and that leads to the signal being enhanced, so it's V1 equals Vs plus Vf. That's going to be amplified in this system by a gain function, which we already talked about, g. So effectively the output signal that we finally get is going to be simply that gain function times V1, which of course is going to be modified by this feedback. That's just a general form of our previous discussion about the change in temperature in terms of the net radiation change. So that signal is picked up by H and a fraction fed back, giving Vf equals Hv2. So if you write down all the equations here, the output signal is just GV1. V1 of course is Vs plus Vf, and Vf is just Hv2, depending upon this component here. In other words, we've got these two extra terms, GVS plus GHV2, to take into account. But of course that's just one loop. Let's first of all just write down the output signal, V2, as simply G divided by 1 minus GH times Vs, the input signal. And we're going to take the product of G and H and call it F. And that's what we call the feedback factor of the system. It's the fraction of the warming, based on our discussions, induced by the gain function fed back on the system. So GH is just F, the feedback factor. If we add lots and lots of different loops, let's assume they're independent of one another. They may not be, but let's assume they are. Of course, each of those loops are going to be characterized by a different value of H. Let's call it HI. So Vf is simply the change of the product of Hi and G, and we can call that simply delta Fi. So effectively, the output signal from our system is going to be V2 equals G over 1 minus the sum of all those feedback factors times the input signal. Now in the climate signal, in the climate system we've been talking about, the signal would be delta I, the change in radiation, and the response is going to be change in temperature. In other words, delta T, change in temperature, is G over 1 minus the sum of all those feedback factors times the change in radiation. Or we can simply take this and make it simpler by calling it GF for the whole system. So that's the sort of concept you have to think about when you're looking at feedbacks in a climate system. Okay, so we showed based on that previous reference that a doubling of CO2 would lead to a change in surface temperature on its own of about 1.1 Kelvin. But we mentioned that there are other feedback systems that are going to reinforce or even mitigate that effect. Now we can't go into all of these because they're a topic of ongoing research by climate modelers, but let's think about effects that might reinforce global warming or basically add to the positive feedback. The first one might be melting of snow and ice. What does that do? It's going to lower the surface albedo. That means more radiation is absorbed at the surface. And that ultimately is going to lead to a positive feedback. We increase the water vapor in the air, that's going to reduce the long wave transmission, and it's also going to increase the long wave backscattering, for example. That will then also lead to a positive feedback, more warming in the atmosphere. This is an unusual one which people don't really think about much. If we increase cirrus cloud cover, these are these high altitude 10, 12, 14 kilometer clouds made of ice. Well, if you increase the cloud cover due to those types of clouds, that will lead to a reduction in the long wave radiation transmission, and it will lead to higher long wave backscatter because of the altitude and temperature at which they exist. If we were to continue increasing CO2, of course temperature goes up, means a higher seawater temperature is ultimately what's going to occur. That of course is going to release more CO2. Higher polar temperatures will occur, leading to reduced ocean circulation. We talked a little bit about that. And of course, reducing the ocean circulation and decreasing CO2 absorption in the water is going to lead to a positive feedback. We're also going to get faster decay at high temperatures of organic materials, and that's going to lead to more CO2 and indeed methane emitted, for example, into the atmosphere. Now, plants, of course, do thrive in higher CO2 environments, so if we increase CO2, that's going to increase the growth of plants. Increase the growth of plants, more forests, etc. That's going to effectively reduce the albedo, assuming we don't chop them down. But of course, More plants means generally more dieback in certain times of year, and that will lead to slightly more CO2 into the atmosphere and increase the albedo. So we'll get a much larger fluctuation across the seasons. There are some effects that actually go the other way and mitigate global warming or produce a negative feedback. For example, you know that the adiabatic lapse rate for moist air decreases, and that's going to occur due to increased cloudiness aloft, which of course is going to reduce the temperature. If we increase the temperature, that could lead to an increase in, for example, algal growth in waters, etc., and that will increase consumption of carbon dioxide through photosynthesis, and of course that's going to reduce the CO2 concentration in the atmosphere. But some of these effects are not global, they're sort of regional, and one has to be very careful about taking those into account in models. Okay, talking a little bit about the perturbation and the feedback. Of course, we have to think a little bit about timescales. Remember we said over the last 450,000 years, when the Earth exited an ice age period, the warming was not initiated by CO2. It was initiated by changes in the Earth's orbit and hence the incoming solar radiation. That warming eventually causes the oceans to give up more CO2 to the atmosphere. That CO2 amplifies the warming, which eventually mixes through the atmosphere. So that's our positive feedback. So CO2 will eventually cause warming and maintain and reinforce that warming, and then the rising temperatures will cause even further CO2 to be released. Now, if you look very carefully at this figure, which is based on ice core data, it shows the carbon dioxide concentrations as a function of time. Over here is the approximate temperature change, but it's very difficult to see from this graph, but if you look very, very carefully, it turns out that the changes in carbon dioxide actually lag behind the changes in temperature. And the typical timescales through these natural perturbations is roughly 600 to 1,000 years. That's the sort of typical timescale it takes to see a noticeable effect. Of course, man has come along, and within 200 years, we're starting to do the same thing that takes that length of time to occur. Okay, so let's have a look at radiative forcing estimates for the different components in the atmosphere. Now this is actually based on the original third assessment report. It does say current, but actually it's the then current, if you like. We'll update that in just a minute. And this was based mainly on data published around about 2007 that went into the final AR4 report. So, how do we look at estimates of radiative forcing? Well, what we tend to do is we list all the radiative forcing terms that we think are important. We split them between anthropogenic and natural components. So let's have a look at the main anthropogenic ones. And the main ones are, and of course we're comparing this radiative forcing to pre-industrial times, usually. The main ones are the long-lived greenhouse gases. And the main ones are CO2, N2O, methane, and various halocarbons. So you can see they take up the most in terms of the radiative forcing, in terms of watts per meter squared, around about 1.66 watts per meter squared for CO2, for example. N2O and methane is around about 0.48, and N2O is about 0.16. Halocarbons, due to various drivers and products that they can produce, eventually things like CO2 and methane, they actually contribute about 0.34 watts per meter squared, so not insignificant. Then of course we've got ozone, and we have to be careful here because ozone can be both a radiative forcing positively and negatively. In the troposphere, obviously, it's a warming component, whereas in the stratosphere, it's a cooling component because it absorbs a lot of the incoming radiation. Okay. Then of course we've got stratospheric water vapor. Where does that come from? Mainly from chemical reactions, with the end product being methane, so that produces a small warming in the stratosphere. by and large, that tends to be a cooling region. Then, of course, we've got what we've already mentioned, land use change. That was originally split between black carbon on snow, so if we decrease the albedo, as we discussed, of a nice shiny surface, that will essentially lead to a albedo change that causes a positive feedback, or positive radiative forcing, so it absorbs more. Or we can chop down lots of trees and forests, etc., and of course that will increase the reflectivity of the surface, and of course that's actually going to be a negative reinforcement. Then of course we look at these rather complex components, which we know, if you look at the level of scientific understanding on the far right, LOSU, you can see that these are the ones that are quite uncertain. We have essentially aerosols. Now originally these were combined into total aerosol and then split between what we've discussed previously in the course, the direct effect, absorbing and scattering, and also the indirect effect, the cloud albedo effect, or the Toomey effect. So of course, whilst there are absorbing aerosols, like carbon for example, most of the aerosols tend to be good scattering components, and they tend to essentially produce a negative radiative forcing, so cool the planet. And the cloud albedo effect, of course, also tends to cool the planet. However, what you want you to look at is the error bar associated with these. They're extremely large. The uncertainty of these two combined is even larger than the radiative forcing from carbon dioxide. So that's why a lot of attention is being focused on trying to improve our understanding, which was then low to medium, to try and reduce these uncertainty bars. Also, we want to know what's going on in the stratosphere, because that's a good indicator potentially of what's happening in terms of global warming, in terms of the cooling or warming trends that we discussed in the last lecture. That's slightly positive, for reasons we discussed previously. And then of course we've got these natural cycles, mainly changes in solar irradiance, and you can see that that's actually pretty small compared to all those main drivers. If we add up the total anthropogenic radiative forces, we end up with about 1.6 watts per meter squared. The question is, has that changed very much over the last 5 to 10 years? Well, this is what it looks like in the more up-to-date reports, in R4 and 5. What we're now doing is splitting the radiative forcing components into the anthropogenic and natural as before, but then we're further splitting the anthropogenic into well-mixed greenhouse gases, and then splitting it between the emitted compound and the resulting drivers. So for example, CO2, well, that pretty much stays there for a long time. Methane, however, can undergo some chemical reactions in the atmosphere. It has a lifetime of about 8 years, depending on the kind of reactions you consider. But ultimately, it will also produce carbon dioxide, methane, even ozone, and in the stratosphere, as we mentioned previously, water vapor. Then we've got all those CFCs and halocarbons we mentioned. They can ultimately produce ozone, and higher order CFCs. And then of course we've got N2O, which is pretty inert, but is a very powerful greenhouse gas. And you can see the number for CO2 has changed a little bit, but not very much, to about 1.68 watts per meter squared. Similarly with all the others. And then we've got the short-lived greenhouse gases. So they've got very short lifetimes, but we have to take them into account. For example, carbon monoxide, non-methane volatile organic compounds, and oxides of nitrogen. The problem with some of these trace gases is that they act as precursors to produce aerosols in the atmosphere, like nitrates. So if you look, for example, at NOx, it can have both a positive and negative forcing because it can produce particulates. And those particulates, in this particular case, are actually good scatterers of radiation, so they produce a negative radiative forcing. So all of those have to be taken into account. And then we get back to our good old aerosols and clouds. And we've now split those into, for example, aerosols and their precursors. So we've got nitrate in here again, for example, but we've got the mineral dust, sulfates, organic carbons, but also black carbon as well from biomass burning and anthropogenic burning, etc. Sulfate production, mainly from ammonia, nitrate mainly from ammonia, And then of course we've got black carbon, which is going to be a very good absorber. And then in the bottom again we've got how do clouds adjust to those aerosols, because clouds to form need cloud condensation nuclei, and the composition to some extent, and in particular the concentration of the aerosols, are going to essentially control the cloud albedo, their location and indeed their lifetime, and also in fact their precipitation rate. So if you look at this area, you can see we've got positive and negative forcing from all these different types of particles. Mainly we get warming, as we mentioned before, from black carbon. The other types of particles have got a very large real component to their scattering coefficient, imaginary refractive index, a real part of their refractive index, and so they produce a cooling effect because they're good scatterers. Similarly with clouds, but again you can see the error bars associated with these are still pretty large. Whereas we know how these different particles essentially absorb and scatter radiation, and more or less we know a lot about their concentrations in the atmosphere now, so we have high level of understanding or high level of confidence in those numbers. You can see that cloud adjustments due to those aerosols is still low. In fact, it's the only low one on the list if you look carefully. Again, albedo change due to land use. Now we've actually brought together the black carbon on snow, deforestation, etc. into just one component, and essentially the net effect is to cause a cooling effect, so it's negative. And again, changes in solar radiation. Now as we get more and more data, and we have more and more confidence, as you can see in the final column, what that's allowed us to do is to look at the radiative forcing relative to pre-industrial, 1750, as a function of time now. So this is these graphs show the radiative forcing total due to anthropogenic emissions in 1950, 1980 and 2011 compared to 1750. And you can see that it's increasing 1.57, 1.25, 2.29. So those anthropogenic components over that period have been increasing significantly, and within the area of uncertainty, more or less, based on this analysis. So what I'd like you to do in your own time is to go through these notes, which just summarizes some of those values for radiative forcing for the different components. Some of these have been updated from the previous lecture notes, but always refer back to that previous graph for the actual numbers, because some of them may not have been. So remember, radiative forcing due to carbon dioxide, methane and nitrous oxide is roughly 2.82 watts per meter squared. Its rate of increase during the industrial era is very likely to have been unprecedented for more than 10,000 years. Carbon dioxide radiative forcing has actually increased by 20% from 1995 to 2005 based on the data set from that period, and that was in fact the largest change for any decade in the last 200 years. We've got anthropogenic contributions to aerosols, sulfate, organic, black carbon, nitrate and dust, and they together produce an average cooling effect with a total direct forcing of around about minus 0.27 watts per meter squared. But then of course we've got this indirect cloud albedo forcing component, which is actually much bigger, minus 0.55 watts per meter squared. Now we know a lot more about these forcings now since the third assessment report, because we've got improved in situ measurements, improved satellite measurements, we've got a lot more ground-based measurements, and of course we've got much better models, much better, bigger computers. But as we mentioned, the cloud aerosol adjustments remain the dominant uncertainty in those models. Okay, I'll leave you to read this page and make sure you're familiar with the typical values, which will change depending upon the updates to the AR4s and 5s that are coming out. But the main thing is to remember that this is typically the natural change that we're looking at, 0.05 watts per meter squared due to changes in solar insolation. That's the radiative forcing since 1750 contributed to by that natural change, the external forcing by the sun. So compare all those other numbers with this. And if you can remember roughly the changes in radiative forcing over those periods, we've simply increased over the last half century from about 0.5, 0.6 watts per meter squared to roughly 2.3 by 2011-2012. Now, just to remind you that there are lots of other effects that we still don't know much about. We looked a little bit at these when we considered an aerosol layer, for example, over a different type of surface, whether it be reflecting or absorbing. So, for example, if we have lots of absorbing aerosols in and around cloud, what's that going to do? It's going to increase the amount of radiation absorbed in that volume, and that will actually lead to evaporation of the cloud. So in other words, absorbing aerosols in that scenario might reduce low cloud cover, which of course would warm the climate, because low clouds obviously scatter solar radiation very efficiently back to space. So that's one thing that may need to be considered. There are lots of other effects. These are just one or two examples. The vertical distribution of cloud and aerosol, which we did discuss when we looked at those earlier models. For example, if we were to put absorbing aerosols above a cloud, that's going to increase warming, because we have a nice reflective surface below that layer, so the radiation that gets through is going to be reflected back up into that layer, increasing the absorption within that layer. So that's going to lead to a net warming, certainly of the atmosphere above the cloud. Then of course we might then put the absorbing layer below the cloud, and of course that's going to have a smaller effect in terms of the net radiation absorbed, so we're going to get a net cooling. Now, recall that we said that the radiative forcing concept was criticised because it doesn't take into account the timescales on which some of the forcings occur and the responses occur. And that has been addressed in more recent reports, but again, we don't really need it for the mathematical component of this course. But just remember that the strength of the drivers we're talking about is given as the radiative forcing. It's given in units of watts per meter squared. It's the change in the energy flux caused by a particular driver, increasing CO2 for example. It's normally calculated at the tropopause or top of the atmosphere in models, but in the traditional concept of RF, all the surface and tropospheric conditions are kept fixed whilst the driver is changed, whereas in more recent models a lot of the drivers are allowed to change simultaneously. Now, in calculations of radiative forcing for these well-mixed greenhouse gases, which remember dominate radiative forcing, and aerosols, particularly in the most recent assessment report, number 5, physical variables except the ocean and sea ice are allowed to respond to perturbations with very rapid adjustments, rather than just looking at the end of the model run and assuming that's the final answer. Now, what that means is that the resulting forcing is slightly different. It's what's called the effective radiative forcing. But by and large, it doesn't change the overall picture very much. So the ERF, the effective radiative forcing, which is now preferred, reflects the scientific progress that's being made in understanding the temperature response to all these drivers. Now, for all drivers other than the well-mixed greenhouse gases and aerosols, rapid adjustments are not as well characterized, and they're generally assumed to be small, so we still are able to use the traditional radiative forcing. And use of the ERF has caused generally small changes, particularly in the well-mixed greenhouse gas components of the radiative forcing list. And indeed, this is the sort of effective radiative forcing modelling that's produced. So this essentially shows the effective radiative forcing in watts per meter squared on the vertical axis. So if it's positive, that's going to be a positive forcing. However, they've also split this graph between total, anthropogenic, etc., and natural. So if you look at the green, it's not actually green, my eyes are this orange, I guess, the top one, that shows the effective radiative forcing as a function of time since 1750 up to about 2010 of the solar variability. So you see these small changes. And of course we've got black carbon and snow plus contrails. We've got that stratospheric water vapor, which is the essentially end product of methane being emitted into the stratosphere. We've got tropospheric ozone. We've got these other well-mixed greenhouse gases, WMGHG as they're called, and then we've got carbon dioxide, which of course is the biggest one. So you can see the effective radiative forcing with time. But of course we also have to take into account these cycles of perturbations due to volcanic emissions, which are shown in purple. So you get these big spikes occasionally, but the red line, which shows the total anthropogenic trend, is still upwards. Also shown are changes in aerosol radiation interactions, aerosol cloud interactions, land use change, and of course stratospheric ozone in these different colours, which cause cooling or negative radiative forcing, or effective radiative forcing in this case. So it doesn't change the overall picture very much. So for homework, I would like you to summarise in your own words the main changes in, I suppose you call them the well-mixed greenhouse gases since pre-industrial times, and the contribution of anthropogenic emissions to climate warming and their net impacts. So try and put that down on paper, 1 to 2 pages, if you can. And I would also like you to read some of the following slides to give you some specific topics that you might look at. For example, how these impacts occur, will affect different regions, which are shown in these model results here. So global land, global ocean. You can see the temperature changes as a function of time. And they've also now been split between, using these more recent models, different regions of the globe: Europe, North America, Asia, Africa, South America, and Australia. You see some regions, it's easy to see the contribution of anthropogenic emissions, which are in pink, versus the contributions from natural, which is in blue. The black are the observations, so you can see that most regions seem to agree quite well with the model predictions of combined anthropogenic emissions and natural variations quite well. Some not so well, for various reasons. And again, these models go into even more detail now, because we've now got even better oceanic atmosphere coupling models. So we've even got the ocean heat content, for example, in these graphs here for different oceans of the world, where it's been compared to the air temperature in these yellow boxes again. So now we have land surface, land and ocean surface, but now we've also got ocean heat content. And again, you can see the ocean heat content is also showing an upward trend with time. So go through these various slides, and in particular, ready for next week when we're going to talk about man's use of energy, I'd like to go through these predictions of future emissions, please. So you see there's a list of emission scenarios: A1, A1F1, A2, B1, B2. So please go through these final slides ready for next week, because we're going to talk about man's use of energy and how to predict that towards the end of the century. And the question is there enough fossil fuel to keep us going to the end of the century? If not, where are we going to get our energy from? Another interesting question might be, because we're going to use what's called top-down versus bottom-up approaches to look at the budgets of energy use. My question to you is, what fraction of the energy intercepting the Earth from the Sun can we actually make use of? It's not just a matter of sticking out a solar panel. Remember, the energy in our energy budget graph is split between lots of different components within the Earth system, from wind, etc., etc., etc. What fraction of that can we actually make use of for our energy needs? Do you think we can make use of it by the end of the century, when our population is going to grow? So that means we're going to have to calculate how the population is going to change by the end of the century. How are we going to then estimate the total energy use based on that population prediction? So have a think about that by going through the remaining slides of this lecture, and then we'll start discussing it next week. Thank you for coming.
我觉得前一排不是，我就前一排500一你还是跟他签个书，怎么样？然后他就买了VIP 票，
Has everybody signed in?
Oh no no no.
可以啊，跟 Fernando
差点忘了。
维密星那个。
因为我们。Thank you, thank you.
Thank you.
Mm. 没有吧？之前有个小姐姐不是啊，你记得吗？海哈她前男友的那个，就在第一排，人家不在第一排，在全是海。真的。那个可经典了。我看到了，人家他算什么人？对。他就说什么我的前男友和他的现任女朋友都在现场。可是那个他上面说的不是这样，是他说的是公众号10点发布，但是O2上面9点半才开始发布。那天我们瑞士，你跟康闹，你看他9点半就开始了，反正打拼了，9点半就开始了。他这边写说10点他才发链接。当然不是，他的意思是所有的抢票方式我们都可以抢，反正抢到的票最后都可以照办。真的吗？真的蛮火的。真的很火啊！周杰伦他一共为了周杰伦这个演唱会创了15个人全部买了。但我觉得我们也不应该。